And I thought I did, just because I'd fallen behind in this chapter on talking about reading response questions. I took some from both of the reading response sections in chapter 8, just to very quickly, a lot of you echoed each other's kinds of questions, so I tried to take some of the most popular ones. Here's one that several people asked. If slipping happens while rolling, how does the relation V equals R omega change? So this was for V center of mass equals R omega. That's for rolling without slipping. If something is, not sure you can quite see this on the camera, but if I lower this down a little bit, if something's rolling without slipping, so it's not skidding as it rolls along, the faster it rotates around its axis, the faster the center of mass of this is moving through space. And the question that several people asked is, well, what happens if it is slipping while rolling? And the answer is there can be any relationship between V center of mass and omega that you like. For example, here's a non-zero omega where V center of mass is 0. It's on ice, right? It's not going anywhere. It's just spinning, spinning, spinning. So we've got a non-zero omega, but a 0 V center of mass. Or it could be going along and slipping a little bit, but it's spinning much faster than it's progressing relative to V equals R omega is suggesting there. So, this one question I think I put up here, is there such an equation for such cases? No, because it could be any relationship that you like. You would need more information. So usually we're not going to consider those cases because it's partially skidding. Either it's in pure rotation and the axle is not moving at all. That's one simple case, or it's rolling without slipping, which is only slightly more complicated. But the intermediate cases are hard to think about or require more information anyway. When analyzing torque on an object, is it beneficial to draw a free body diagram? Well, yes, I guess I didn't really say this, and I'm not sure what we've been drawing free body diagrams of a sort. Sometimes I call them extended free body diagrams. I'm not sure if Giancoli has a name for them, but up before this chapter, we kind of didn't really care too much what shape we drew for a body. This might be a suitcase and I just draw it as a sphere, right? And we say, oh, okay, I've got a normal force and I've got a weight force and maybe there's a friction force. Well, now when we're concerned with torques, we have to carefully specify exactly where the force is being applied. So, I would still draw a free body diagram, but I might call it something like an extended free body diagram. And that is, I draw something that's a semi-realistic representation of it. Okay, I've got a meter stick, right? And I'm applying a force up here, and gravity is applying a force down at the center of mass, and so on, right? So it's just a slightly more detailed free body diagram. So yes, we are doing that. Does the axis of rotation have to be in the center of a plane being rotated? I know it doesn't have to be in the exact center, since the example Monday, I had that cutout of Kentucky. And, actually that happened to be at the center of mass of my cutout of Kentucky, but it didn't have to be, right? Just like this particular cylinder here could rotate about its center of mass, but it also might not. And that problem I was referring to, could just spin around its center of mass, which is at the center of symmetry of this. But it could be rotating around in a circle, like flopping around like that, rotating around a fixed axis that's not the center of mass. So no, it doesn't have to be. Usually the axis is somewhere on the object. I mean, I suppose it's in principle capable of imagining the axis is over here and it's in rigid rotation around it. There would have to be some feather-like thing connecting it to the axis of rotation to make sense of how it's doing that. But in principle, it could be. I'm confused by the statement, for rotational motion, the mass of an object cannot be considered as concentrated at its center of mass. I believe what this is referring to is in calculating, I mean, we do that sometimes in rotational motion, right? When we're calculating changes, if I have an axis at the end of a meter stick and we're going to let this thing flop down, rotating about the axis, we do pretend that the mass is concentrated at the center of mass of gravity for the purpose of calculating the change in potential energy. So it is useful there. We also pretend it's concentrated at the center of mass for the purposes of calculating torque at any position, right? If this is my axis down here, maybe at a later time, it's moved down a little bit and the center of mass is here, right? And we just pretend all the mass is concentrated there as far as gravitational torque is concerned, and we consider the corresponding moment arm there. What I believe Giancoli is referring to, I didn't see the exact quote there, is that we can't do the same thing for moments of inertia. For example, I might say, here I've got a meter stick and it's pivoted to rotate about an axis at the center. And suppose, so it's got some moment of inertia, which I believe is 1/12 ml squared. This is one that's in our table, right? A rigid rod, thin rod that's pivoted to rotate about its center of mass. That's 1/12 ml squared, where L is the length of this. If we pretended all that mass was just concentrated at the center, it would have zero moment of inertia at all, right? That the mass has to be separated from the axis of rotation to get a non-zero moment of inertia. And so here's a case, and this is generically true, that you can't calculate moments of inertia by assuming the mass is all concentrated at the center of mass. It would be nice if that were the case, but it's not that simple. I'm still confused on rotational inertia. I thought inertia involved mass, so why doesn't the mass of a rotating object matter when looking at rotational inertia? And why does it involve diameter? So first of all, the mass matters, and it does come into the table formulas, right? Those 1/2 mr squared. It depends on the mass of the object. And generally, you keep the axis location the same and you double the mass, you'll double the moment of inertia. So it does depend on that. But it also depends on the size of the object, and why that's the case. We talked about torque and moment of inertia sort of indicating when I start rotating an object, how hard is it to get it into a state of rotation? In other words, how hard is it to angularly accelerate an object? So let's imagine that I compare two cases. For example, I've got, here's where my hand is, and I'm going to rotate about an axis, which is where my hand is, and I'm holding a rod. The rod's almost massless, but I'm going to put a really heavy mass on it somewhere, right? I'm going to do two cases. So this is a very strong rod, but it has almost no mass. Let me put this, maybe 10 kilogram mass really close to the axis. Now, when I start moving it, let's say I start moving it at 1 radian per second, and it takes me 1 second to get it up to that speed. After it's up to that speed, this, 10 kilogram mass will be moving at some modest speed. I will have accelerated it to a modest velocity with a certain rate of angular acceleration. Now imagine sliding that 10 kilogram mass so that it's 100 miles away out on this rod, right? And I just move it at a modest rate of angular acceleration, and all of a sudden, this 10 kilogram mass that's miles away has been accelerated to 100,000 miles an hour, just because it's such a great radius away. So it's going to be much harder for me. It has to be much harder for me to start to get it moving at that rate, because linearly, I have accelerated it to a great speed, right? Whereas in the other case, where it's close in, this is the case where the moment of inertia would be small. The mass is close to the axis. If I make the moment of inertia huge, that means it's got to be hard for me to get it going, even at a modest omega, because the real speed associated with that, I'm going from 0 to that speed, is some huge change. And I've got to do a lot of work for that to happen. So that's maybe one way to make it a little bit more intuitive why it matters where the mass is, how far it is away from the axis. Probably too many of these reading response questions up here, but one more just to finish them out. Do you have to find, we didn't talk about center of gravity in class, but a lot of people asked about center of gravity and the relationship to center of mass. Do you have to find the center of mass to find the center of gravity, or is there a separate equation to find the center of gravity? Since they are equivalent in nearly all scenarios, I would assume you could find the center of gravity the same way you found the center of mass. Well, center of gravity is kind of more complicated. At the surface of Earth, for small objects, the center of mass is located where the center of gravity is. The center of mass is sort of like, well, I guess you could think of it as defined by the equation we had. How does the center of gravity differ? It differs in, let me imagine a scenario. Here's the entire Earth. Let me unshare the screen since I'm drawing. Okay, so here's a huge mass, Earth. Here's a huge meter stick. Okay, it's not a meter stick. It's a many, many thousands of kilometers meter stick, right? And I'm gonna, so it's a rigid rod. It's got some mass. Let's assume it's uniform all the way across. And I'm gonna, right in the middle, put an axis of rotation. Now, if you believed that you could calculate the gravitational torque on this by just pretending all of the mass was concentrated at the center of mass, which is right on the axis, if you believe that, then you would conclude that this thing should start rotating. Hopefully it's clear to everyone that it is going to rotate, right? Because there's hardly any gravitational force on this side over here, whereas this side is feeling a huge force downward, right? So instead of finding a way just to look at mass and ignoring what the gravitational field is, it's sort of like the gravitational field, little g is very small over here. Little g is much bigger over here. The center of gravity is finding out where the gravitation, instead of replacing all the mass with the mass located at a point in this concept of center of gravity, we divide up, we think of there's lots of little forces on all little bits of mass. Where could I place one force so that the overall dynamics of it don't change? And in this case, I would have to place that force sort of near this end, and it wouldn't be at the same place as the center of mass. So the only place where they differ is when the gravitational field over the surface, over the span of your problem really changes a lot. So if I'm talking about a meter stick here at the surface of Earth, little g is about the same everywhere in the experiment I'm running. And you'll find out in that case, the center of gravity is the same location as the center of mass. But in the case where some things are really near a strong gravitational source and other parts of the object are far away, they're slightly different. And the center of gravity is the more relevant thing to use in terms of calculating how it's going to start rotating. Any more questions on those? That's just to wrap up chapter 8. Although we're going to continue talking about the same kinds of things. And our goal today is really to work through a lot of practice problems in chapter 9. And chapter 9 is kind of a follow-on to chapter 8. So for those of you on Zoom, I think I posted under today's date on the website. You can go grab that worksheet if you don't have it. For those in the classroom, I apologize. I forgot to hit the staple option when I did this. It's actually a 2-page worksheet. So you're going to get 2 unstapled pages. So, which there's so many of them, it's hard for me to separate them. But there's one set. Here's another set. One set. Here's another set. If you're on Zoom, it's got a seesaw image on the first problem. And we're going to talk about today the conditions for static equilibrium, which you talked about in lab this week, right? Not only that the sum of the forces, of course, on an object have to be 0 for it to be in static equilibrium, but the sum of the torques about any axis that you might choose has to be 0 too. Okay, so let's see if this is working. Right, so the discussion I hope you had at the beginning of lab, this is kind of how I started the idea. Of course, if I have a meter stick and I say it's just sitting there, it's not accelerating, of course, since the sum of the forces on it equals ma, if something's just sitting there, its acceleration is 0. Now, if it's moving, there might be lots of different accelerations if it's rotating for different parts of the object. But if an object is in static equilibrium, it's just sitting there, and that means that the acceleration is 0. And so one condition is that the sum of the forces have to be 0. And when I say the sum of the forces have to be 0, that means the x components have to add to 0, the y components have to add to 0, and the z components, if there is such a thing in your problem, have to add to 0 too. That's what it means for the sum of the force vectors to be the 0 vector. Clearly, that's not enough, as hopefully you found out in this week's lab. Here's a situation where we're out in outer space, here's a meter stick, and I apply equal and opposite forces, but to different parts of the object, and it's not going to be in equilibrium. Everybody knows it's going to start rotating, right? So we need an additional condition for static equilibrium, and that is, if it's going to be in static equilibrium, I can actually choose any axis location I want. Notice there's no given axis of rotation in this particular problem, and we'll see how that plays out in the problem solving we're going to do. But it's pretty clear that we don't want it to rotate at all, and therefore the sum of the torques have to be 0. And we'll see how we can choose the axis to actually make our life easier in terms of the algebra that results, okay? You just have to kind of reassure yourself that you could justify, I'm not going to show it here, that if both of these are satisfied for one axis I choose, then it's going to be true for any other axis I choose. So if the sum of the forces and the sum of the torques are 0, and I've chose the axis to be at the left end of my meter stick, it would be true for my axis at the center or at the right end. So it really doesn't matter what axis you choose. You do it to make your life easy. Okay, let's start off with an easy case. Here are two kids sitting on a 40-kilogram seesaw board, which is pivoted at the center. So the mass of the board itself is 40 kilograms. This child on the left, 30 kilograms, is 2.5 meters from the pivot point, so 2.5 from the center. And the child on the right is 25 kilograms, and at least in part A, is sitting at a position so that it's balanced. She's got less mass, so she's got to sit a little bit farther out, right? When the seesaw is balanced, what force does the pivot exert on the seesaw board? And if the child on the right has a mass of 25 kilograms, how far from the pivot should she sit to make the seesaw balanced? So why don't you just take a minute, these aren't complicated calculations, but think about those two conditions. Maybe you'll use just one of them, maybe you'll use both of them. But if I want to figure out the force of this little triangle pivot here on the board, how hard does it have to push up on the center of the board when it's balanced? How could I calculate that? And then how far away from the center does the child on the right have to sit? I guess this is an easy case because there's an obvious axis that you would choose, right? I mean, if you're going to consider an axis, it seems like the center pivot is the obvious one. That won't be true in later problems that we do. So if you're having trouble getting started, draw an extended free body diagram for the forces acting on that board, the piece of wood that comprises the seesaw. There's an upward force from the pivot and two downward forces from the kids' weights. Okay, let's go through them together just to quickly show. I guess we can just do the work on the board. I've drawn what I might call an extended free body diagram for my object here, showing not only the forces acting in their directions, but where they're being applied. 25 kilogram weight force, a distance x over there, 30 kilogram, a distance 2.5 to the left. And we want to know that pivot force that's going upward. And to answer A, what is that pivot force? How big is it? It suffices to just say, let's do this, let me put some coordinates on here, x and y. The sum of the force y components certainly has to be 0. Sum of the force x components has to be 0, and the torques have to be 0. But this is one thing that has to be true, and that's going to involve my FP. So expanding this out, I get FP minus 30 times 9.8 minus 25 times 9.8 equals 0. And that allows me to solve for the pivot force. I don't have my calculator, but we'll see what it is, hopefully here. And you can tell me if you agree with this. There we go. When in mine, I forgot the weight of the seesaw board. I was asleep at the wheel. It must be Friday. Yes, there's also another force that is effectively being applied at the center of mass. I forgot that we have a mass for the board too. It's 40 kilograms, so we have a 40 times 9.8 going down. I was sort of thrown off by my own solution here. Where did this come? Oh yeah, that's right. That's the seesaw mass. So it should be shown going down at the center of mass. So it's being applied downward at the pivot. But in any case, the sum of those 4 in this case has to add to 0. That allows me to immediately solve for the pivot force. So it's pushing up with a 931 Newton force. If the child on the right has a mass of 25 kilograms, which it's suggested in several places, how far from the pivot should she sit to make the seesaw balanced? Well, in this case, summing up the torques has to be 0, right? Moving the position of the second child in and out isn't going to change the net force, but it will change the net torque. And so we want the net torque to be 0 if it's perfectly balanced, in other words, in equilibrium. So I'm going to do, in this case, it's pretty clear the axis that I want to sum torques about, right, is the place where it's going to rotate. And there's not too many other tempting places. We'll see that there are in other problems. So the sum of the torques have to be 0. That's what torque net means. And let's see, there are 4 forces acting here, right? There's a downward force from this child. If I didn't really draw an axis positive direction, but let's take counterclockwise, the direction I'm moving the laser pointer now, that direction to be the positive rotation direction. So then this force is going to be a positive torque. Everybody okay with that? That's why I'm putting a plus sign over there. And it's the magnitude of the force times the moment arm, right? The force is going in this direction. So I draw the line, can't say this too many times because people forget it. Draw the line that contains the force vector to find the moment arm. And then say, what is that shortest distance to the rotation axis? That's 2.5 in this case, right? The moment arm for this one's torque is going to be x that we're going to solve for. And the moment arm for the missing 40 times 9.8 going down there, its moment arm is going to be 0 if I choose my rotation axis to be there. And the moment arm for the FP is going to be 0 too. So in terms of the net torque, even though there are 4 forces, these two generate 0 torque because their moment arms are 0. Back to the solution here. So I add those two together, and of course the moment arm for the one on the right, first of all, that torque is negative, given the, if I'm taking counterclockwise to be positive, this torque is trying to twist it in the clockwise direction. So that's what I said is negative. I should have probably drawn that in my solution. And since those add to 0, the only unknown is x. I can solve for x. X has to be 3, of course. The lighter child has to sit a little bit farther out to balance. You know that probably somewhat intuitively. Any questions on that? That's our starting problem. Easy one to start with, but they're going to get more confusing very quickly. But first, a voting question. Here is a meter stick, and we haven't placed the pivot at the center. We've placed the pivot at the 25 centimeter mark, a quarter of the way from the end, right? And so the meter stick is balanced in this case. It's in static equilibrium. We're told that the mass of the rock that's being hung right from one end, that short end, is 1 kilogram. And what is the mass of the stick if it's in equilibrium? You can imagine if the stick were really heavy, it's going to flop down to the right? The right side's going to go down. And if the stick's really light, then it's going to flop down on the left side, right? The rock's going to win out. And if it's just heavy enough, just massive enough, then it will be perfectly balanced in between those cases. Let's see a vote on those. Think about it for a second. All right, I'm not sure where people are at, but if you got a vote, hold it up. Let me just see for the fingers and cards where we're at. If you're really unsure, you don't have to vote. For the ones I'm seeing, it's C's and D's, either 1 kilogram or 2 kilograms. Anybody want to explain their thinking on this? Well, let me ask first, how many forces are acting on the meter stick? If you had to count them up in terms of the kinds of forces we've talked about in this, there's no air resistance force because it's not moving, but other kinds of forces. There's a string force, right? There's a force up from the pivot. What else? A gravitational force, right? And what do we know about computing torques due to gravitational forces on extended objects? Yeah, we can just pretend all the mass of this entire meter stick here is located at the center of mass. And the center of mass is right there, right? So if the force is going to go down there, right? Now, the pivot force, though it's going up, isn't going to cause it to rotate one way or the other. It exerts zero torque about the axis where the pivot point touches, right? So the only forces that matter for the torques are this one's trying to rotate it counterclockwise, right? It's trying to pull it down over there. We need another force over here that's going to balance it at the center of mass, and that's 25 centimeters away from that point too. So wouldn't a 1 kilogram force there work too? So the answer is 1 kilogram in that case, because we're going to pretend all of that mass is concentrated at the center of mass, which is the center of gravity, since we're doing this experiment near the surface of Earth, not near a black hole that's near one end of the meter stick or something like that. More discussion on that one? Yeah, Abby.
Okay, so my thought process was not physics at all. But I was thinking like 2 kilograms, because then the meter stick is divided into 4s, which would make each fourth like 0.25 kilograms.
Yes.
So the 1 kilogram rock plus 0.25 on that side would be 1.25, and then 0.25 times is not 1.25. Never mind. It's 1.75.
Yeah, so for those of you on Zoom, Abby's sort of arguing through she was breaking, instead of, I would say the difference between what Abby was explaining and what I just explained is, I'm treating this entire meter stick as one thing and its center of mass is there. And she, like many people are tempted to do, is breaking it up into 4 pieces and kind of separately thinking of the mass of these 4 pieces. And then, sometimes people think, well, okay, this 4th over here is kind of balanced out by this 4th over there. So these 2 pieces together have to balance out this. Now that's kind of complicated, because then I'm going to think, well, okay, their center of mass is of these 2 rightmost pieces is right over here, and I've got to figure out its moment. Now it'll all work out the same way. It would still have to be 1 kilogram, but the mass of these 2 pieces would have to be 1/2 kilogram if you placed it there, and it's going to balance out just the rock. But it's much easier to think about it just in terms of the center mass of the whole thing. It doesn't matter that some of the mass is, on one side of the meter stick and some of the mass is on the other. You still just look at the entire meter stick and pretend it's all located in center of mass. So it's simpler maybe than you're thinking it might be. Other questions or comments on that one? I like that question because, a lot of people kind of think the same way in terms of treating the stuff on the left differently than the stuff on the right, but it simplifies your life a lot to just treat it as one object. Okay, here's a significantly more complicated situation. This is kind of an idealized diving board that's not bending at all. So it's a rigid diving board that's completely flat. And there's sort of a 2-part pedestal. We've got 1 vertical piece attached to the very back end of the diving board, and then 1 attached somewhere approaching the middle. And then a diver of a certain mass, we're told the mass up here, or not the mass, but the weight. Diver has a weight of 500 newtons, and we're told various distances here, and the mass of the diving board itself, or the weight, is 142 newtons. And the question is, what forces that the pedestals A and B exert on the board? In other words, what force is A exerting on the back end of the board, and what force is B exerting on this end of the board, including their directions, right? Are they pushing up, or are they pulling down, or a little of both? Let's just draw an extended free body diagram, and then I'm going to leave you to kind of answer, or at least think about the forces. Let's see, if I stop share, I'm just going to try to draw it. I'm going to bring up I've got my thing here. I just need to see what the numbers are. So let's draw an extended free body diagram without all the graphic elements in it. We're just going to draw the board itself and try to put the relevant distances on it. So here's my diving board. The diver has a weight of 500 newtons. So we're, idealized sense, we're going to imagine the weight is at the very end of the board. There's a 500 Newton force going down. At the very center of the board, we're going to pretend that all the mass of the board, for the purposes of calculating torques, is concentrated there, right? And so that's 142 newtons going down there. Gravity always pulls down. And what are we told about that? We are told the board is 4.48 meters. So if this is 4.48 to go from there to there. And that means, if you like, this is 2.24 meters from there to there. It's halfway across the board because it's a uniform board. And then A and B are exerting forces on it. And honestly, I don't really know if they're up or down forces. It seems like maybe they would both be pushing up. They've got to support the weights of these things. So let's imagine that they're both up. And we'll find out that if we solve for them and we get a minus sign, we'll know we guessed wrong, right? If I draw an FA up here and I draw an FB up here, if FA ends up positive, but FB ends up negative, then I'll know that the real direction of FB should have been down. Normally these are the magnitudes of these forces, but if my magnitude ends up being negative, that means I should have actually drawn it in the other direction. So that's my extended free body diagram. I guess I also need the fact that this is 1.55 meters here from there to there. And I think that kind of gives all the information that we're given in terms of distances. And what do I have to work with? Well, I know it's in static equilibrium. Nothing's accelerating, nothing's rotating, and so the sum of the force x components have to be 0. I haven't put an axis on here yet, any axes, so let me put x and y axes. X, y. Now, it is true that the sum of the force x components equals 0. There's nothing going on in the x direction, so that's just going to be 0 equals 0. I don't need to write that down. But the sum of the force y components has to be equal to 0. You can write that down. And it's also got to be true that the sum of the torques has to be equal to 0. But unfortunately, when I calculate torques, I've always got to calculate them relative to an axis. And here, there's no obvious axis of rotation. Nothing's going to rotate, right? If this is a rigid board, nothing's moving. So you can choose your axis. Now, notice that for all these forces, we happen to conveniently have been given the distances from the left end. So for the purposes of calculating torques, it's going to be really convenient to take my axis about which I calculate the torques to be the left end, because I know the distance of all the forces from there. I have enough information to find the distances of everything from the center of mass, but I'd have to work at it to do it. So let's just try to be lazy about it. Take our axis there, and for the purposes of calculating torques, I need to know which ones are positive and which are negative. So, why not just arbitrarily say I'm going to call counterclockwise torques positive and clockwise trending torques to be negative. Okay, with that, what I want you to do is write down these two equations. We've got two equations. We have two unknowns. Hopefully we can use it to find those two unknown forces. And remember to think about, if you get a minus sign, that's telling you something. It's telling you guess the direction of that force exactly opposite the real direction it's going. Okay, you're probably on your way. You may not have gotten to the very final answer, but hopefully you've gotten a start to it. Sum of the force y components equals 0. Well, there's just four things to add together. Two have positive y components, or come in with plus signs, and the other two come in with minus signs. So I would have something that looks like FA plus FB minus 142 minus 500 equals 0. And that tells me that FA plus FB has to equal 642 newtons. And that's great. That's a piece of information. So now I know if I get either FA or FB, I'm good, right? Then I can get the other one from that. So we're halfway there, even though we don't have the satisfaction of getting anything definite yet. Sum of the torques. Now I've chosen this axis just out of laziness because I knew the distance of all the forces from that axis, and that's going to help me with the moment arms. Now for the assumed force directions, well, let's first talk about FA. What's the torque due to FA about this axis? 0, because the moment arm is 0, right? I draw the line that contains that force vector and say, how far is it to the axis? 0. So that would be a, if I really wanted to put it in there, I'll say 0 plus. How about FB? Is it generating a positive or negative torque in my axis direction? Positive. Is trying to twist it around in the positive direction. And again, I'm going to do the magnitude of the force times the moment arm, which is 1.55. So that's going to be plus FB times 1.55. Just leaving out the stuff in SI units. Positive or negative torque? Negative. Both of these are negative. They're trying to twist it in the negative direction in my convention. Okay, so that's minus 142 times its moment arm, which is 2.24, minus 500 times its moment arm, which is 4.48. And the sum of all 4 of those torques has to be 0. That allows me to solve for FB. And I get FB is 1650. 1650 newtons. Positive, so that means B is pushing up, like we guessed. Then I go over here, substitute in FB, and we see FA is definitely going to be negative, right? When I subtract off 1650 from both sides, FA is going to end up negative, and after we substitute in, we get FA is minus 1008 newtons. And that means I should have really drawn FA going down, or at least I conclude that FA is going down. Can anybody think of why you might have figured out that FA had to be pulling down and not pushing up, just from, you know, your experience in looking at things like this? What would happen if FA, you know, I didn't glue it or screw it in there, so FA wasn't attached? This whole thing is going to tilt around B and go down like that, right? So A has got to be over here holding it down to keep it from rotating around B in that direction, right? Most people have that kind of intuition about it. So it makes sense that it's negative. Any questions about that one? That's a step or two up from the last one. Especially, you know, not for the least because it doesn't have a definite axis, but, you know, in this case, all the numbers were sort of pointing back to here. So I took the path of least resistance without thinking about it too much. Let's see if I think we're straight on into another problem now, which is the next one involving a sine. Oh, I forgot I've got my solution in there. We'll post those on the website eventually. I'll be forced to once the exam gets closer. Okay, it's not a sine. I'm not sure what it is. There's a mass. Maybe there's a lantern here, looks like, you're right. It's a really heavy lantern. 300, okay, so the beam here, this is a metal beam. It has a mass of 300 kilograms, and it's attached to a wall, except there's a frictionless pivot here. So if this cable weren't up there, this whole thing would rotate around, slap into the wall down at the bottom, right? We've got a light cable, so we're going to ignore the mass of this cable, but that's what's keeping it from rotating down. It's keeping that beam horizontal. And we're told that this angle, you know, we could attach it either at a very slight angle or way up on the wall, but the angle it makes with the horizontal bar is 25 degrees. And here's a light fixture, 100 kilograms, that's hung from the very edge of the beam. And the whole thing's in static equilibrium. So we know in some sense the sum of the forces and the sum of the torques on something has to be 0. What do you think a reasonable something to use in this problem would be? What are all the forces and torques kind of acting on in this case? I mean, there's a lot going on there, and the forces are being pulled on lots of different things. But, to me, it seems like, okay, the wall is exerting a force on the beam through this pivot. The light, through gravity is pulling down on one edge of the beam. The cable is pulling on the beam. It's also pulling on the wall, but, lots of forces are attached to the beam. So just like my, diving board was in equilibrium here, the beam has got to be in static equilibrium. It's just sitting there. If I have too big of a tension in the cable, it's going to pull that beam up, start it rotating. If I have not enough tension, it's going to let it sag down. So what is just the right tension to keep it in static equilibrium there? Find the tension in the cable, and the wall is exerting forces on the left end of the beam through this pivot right there. And you can imagine, well, it's got to have both horizontal and vertical components. Imagine that I just removed the pivot. So I took out the pin there and let this thing in, and we somehow didn't have any friction on the wall. Well, of course, the left end of the beam is going to slide down the wall, right? Does everybody have that intuition? If we remove the pivot thing attaching it to the wall, that beam would want to slide down the wall. So the pivot's got to be pushing up on the left end of the beam at least. But it's also partly going to be pushing out on the beam. In other words, if the wall weren't there, the tension from the cable would kind of push the beam into where the wall was, right? If I removed the wall, that cable tension is going to pull the beam so it gets pushed into where the wall was. So the wall is also pushing out on the beam to the right. So there are kind of two force components. And here is an extended free body diagram, just looking at the beam part of it, right? I've got the weight of the lamp, I was going to say a lantern, but lamp going down there, the weight of the beam itself, located at the center of mass. I've got a tension force, which is going up at that odd angle of 25 degrees in that direction. All those are forces on the beam. And then I've got both horizontal and vertical components that this pivot has to be exerting on the beam. It's holding it out, but it's also holding it up. And I want to find both of those force components. That's what we're talking about, the horizontal and vertical force components. So here we've got three unknowns. We want to know T and that F, what I've labeled as Fx and Fy, the force components, horizontal and vertical from the left end. Well, that's good. I've got three equations to work with. The sum of the force X components has to be equal to 0. Sum of the force Y components has to be 0. And the sum of the torques about any axis I choose has to be 0. And you'll find out, still, again, you can choose any axis you want. It sort of seems to make sense to use this axis. And you'll actually find out that the sum of the torques equals 0 is a really simple equation, because what's the moment arm for the force component Fx relative, if I choose my axis of rotation to be there? It's 0, because it's going right through the axis. Same thing with Fy. So neither Fx nor Fy is exerting any torque on the beam, right? Pushing out on the beam doesn't try to make it rotate. Pushing up on the beam at this location isn't trying to make it rotate around that point. So their torques are going to be 0. And that means the only unknown force that's going to come into the torque equation is that T. Why don't you take a few minutes, see if you can write down sum of the force X components equals 0. I chose some axes there. You don't have to choose these, but horizontal and vertical would definitely make sense here. Sum of the force X components is 0. Sum of the force Y components is 0. And the sum of the torques about that axis is 0. Here I snuck in something, maybe this is typed in your version, a 2-meter long beam. Originally, I didn't put in a length there, but to calculate the torques, you need the length of the beam. So that means the center of mass is 1 meter away from the pivot. Okay, I know you haven't had enough time to do it, but we got about 3 minutes left, so let's just go through the solution and then we'll call it a day. There's one more problem involving bicep holding a weight, you know, with a forearm on the next page. We'll do that on Monday. Okay, so I'm going to choose my axes to be to the right and up. That's X and Y. And then you'll also see that I have chosen, doesn't matter, you could have chosen the opposite direction, but I chose counterclockwise to be the positive rotation axis. And I chose my axis to be at the left end of the beam. So here is the sum of the force X components, which I'm going to set equal to 0. Fy has 0 X component. These two weight forces have 0 X components. So there are only 2 of the 5 forces shown that have non-zero X components. Fx comes in with a plus sign in my coordinate system. And I've got to find the horizontal component of t. That's t times the cosine of 25. It comes in with a minus sign because it's pointing more or less in the negative X direction. We'll have to hold on to that equation. It's got 2 unknowns in it, right? Tension's unknown and Fx is unknown, but we'll just hold on to it. Some of the force Y components, 4 of those are non-zero. Fx has a 0 Y component, but let's see. Fy comes in with a plus. These 2 weights come in with minuses, and t comes in with a plus. It's t times the sine of 25. That is the Y component of the tension. So those 4 things have to add to 0 again. 2 unknowns in there, Fy and t. So now we've got 3 unknowns between these 2 equations. We'll hold on to it. That's why I underlined it. And finally, let's find the net torque with the positive convention that I've given there. The torque contribution due to Fy is 0 and due to Fx is 0 because they have 0 moment arm. In my convention, both of the weight torques are negative, right? So I get 300 times 9.8 times its moment arm, that's 1 meter. That's this piece, and it's a negative torque. And the lamp is 100 kilograms times 9.8 times its moment arm, which is 2 meters, and it's also a negative torque. So I put that minus sign in there. And then for the torque due to T, instead of using force times moment arm, that would be a little bit confusing, at least at the beginning. We can figure it out, but I'd have to say, draw the line that contains the tension, that would be the line of the cable, and find its perpendicular distance to the axis of rotation. That looks a little bit confusing. So let's not do it that way. Instead, I'm going to use one of my other torque formulas, which is the perpendicular component of the force, that would be T's Y component, times the full R direction. So R times F perpendicular. That's 2 meters times the perpendicular component of the tension is T sine 25, the vertical component. It's positive because it's trying to twist it in the positive direction. So all those have to add to 0. That's great because my third equation only has 1 unknown in it, and I can solve for T. 5,800 newtons is what I get, and then I substitute my T up into these 2 equations up here, and I can separately solve for Fx and Fy. The numbers aren't that interesting, but it's kind of interesting to see. You know, this is the kind of thing where you're getting into, it's a very pared down engineering problem, but, you know, engineers have to worry about much more complicated things, and that all the forces, the cable you're using is strong enough and all that kind of stuff. So this is the very first step into an engineering kind of problem. All right, looks like we're over time. So have a great weekend. That homework again was extended yesterday through tonight. If anybody has a quick question about it after class, you're welcome to stay. Man, I wish this were the 3-day weekend. Wouldn't that be nice? 2 more weeks, is that what we have? I think it's in 2 weeks, right? I'm kind of confused why they put the last break day so close to finals. It seems like it would have made more sense to be more in the middle of the term, but that wasn't my decision. You too.